It is a pleasure today to have here with us Mercè Romero-Gómez. She is now a researcher in the Instituto de Ciencias del Cosmos de la Universidad de Barcelona. Mercè did her PhD in the Universitat Politècnica de Catalunya under the supervision of Josep Mas Demont and also Lia Tanasula from Marseille, on the study of the formation of spiral arms and rings around galaxies. Is most of all a theoretical work, also with a part of these models, simulated models and test particle models. After her PhD, that got an excellence award in Spain, she moved to the University of Marseille, the Observatory of Marseille, to work as a postdoc under the supervision of Lia Tanasula for 2 years. And after that, she moved back to Barcelona, where she's now working under inside the group, the Gaia team in Barcelona, and doing several different research on different topics, all of them related on comparing theoretical models with this new data from Gaia. So today she's going to talk about this, just observations by Gaia with the new early DR3 about the Magellanic clouds. So Mercè, when you want, please, you can start. And for the audience, if you want to ask questions now today, yes, you can unmute yourself in the middle of the presentation, so you can do it if you want. Okay, so thank you, Mercè, and you can start when.
I'll start sharing my screen. So let's check again that everything works. So you should see my full screen with the presentation.
Yes.
Okay. So thank you very much for the invitation. So when Santi contacted me about a month ago, and if I wanted to give a seminar to the institute, of course I accepted at the very first moment. But then when I think, okay, what I'm going to present to these people that have not heard before. So since it was so close to the release, to the third release of the Gaia data, and we had published some verification papers, I decided that I could explain you with a bit more detail than we did in the release day of one of the papers that I have been involved. So today I'm going to talk about this paper, but not only this paper, because you can probably have read it, but also I'll try to put it in context on just a biased view of the studies or the works we can do on the Magellanic clouds, or the things that, from my point of view, still need some dedication. So most of the talk will be from this paper, but at the end I will focus on other works and with a summary on ideas on how to go on with the study of the Magellanic clouds. Okay, so we have this image from Laurent Chemin, one of the authors of the paper, a member of the IPAC, of the Large Magellanic Cloud. So the idea in this paper is to use the data from EDR3, so the astrometric data and photometric data recently published, to study, to try to characterize and constrain properties and see the capabilities of Gaia to characterize and constrain properties on the Magellanic clouds. The Magellanic clouds are our neighbors. They are very visible in the southern sky, and they've been a focus of thousands of research works. But let's see how can Gaia contribute on this topic. We also chose to target the Magellanic clouds because they are a kind of a challenge for the Gaia astrometry. As you know, Gaia is obtaining positions, parallaxes, and proper motions for more than 1,000 million stars, but mainly focused in the Milky Way. And we know that we also observe objects outside the Milky Way. But the farther we go from the solar positions, the uncertainties grow. We get fainter magnitudes, and the uncertainties are larger, the parallaxes are less usable. So this was a bit of the motivation. So how we can challenge Gaia with our neighbors, which are not inside the Milky Way, but they are very clearly visible, and we can distinguish different populations in these galaxies. So the first thing we did is to choose different samples. Since we have the photometry, we can try to select different tracer populations. So first we selected the samples centered at the centers of the clouds, looking into the literature and finding what are the most accepted center for each of the clouds. And then we made some selections and with some filters to try to remove as much as possible the contribution from the Milky Way. You can see you can see my mouse, right? On the top left panel, this is the center on the LMC. We can distinguish this is a density plot. The galactic bar, or the bar of the LMC with this very nice spiral, and on the bottom right corner we can start hinting the presence of the SMC. We decided to include to make a large radius around the LMC. And on the bottom right, we have just the same strategy, but now centered on the SMC. And we can see this wing on the bottom left corner of the SMC, which is the one that connects with the LMC. So for each of the galaxies, we can perform these color magnitude diagrams. You can see this is just apparent magnitude in G with the two Gaia colors, the blue and the red, and you can see very nice the main sequence, the giant branch, the red clamp. So we decided to make just very tight cuts on the color magnitude diagram. To have a broad tracers, broad evolutionary phases differentiating different populations of each of the clouds. So, of course, the limits of these polygons are different from each of the clouds, but we try to obtain the same kind of populations in each of them. When I will talk about the young sample or the young evolutionary phase, it will refer to the subset containing this young 1 and young 2, so the upper main sequence. And the red clamp, it is clear, this all the sources within this polygon here around the red clamp. I also want to show you, so now we can go back to this previous plots. These are just density plots taking into account all sources within these regions in the sky with some certain astrometric cuts. And now that we have selected different evolutionary phases, we can, the first thing we did is try to see how these density plots change as a function of the evolutionary phase. So the people in Outreach made a very nice movie with these evolutionary phases. So you can see here that the bottom left we have the LMC, at the top right we have the SMC, and now we change the colors depending on the evolutionary phase. So in blue we have the upper main sequence, so the young stars. Now we had the blue loop. Now the rest of the main sequence, so it would be young 3. Now we go into the red giants. Now you can see that how the different evolutionary phases show different parts of the galaxy, how well or how well or not the spiral lines are traced, for example. And so now we go to the tip of the asymptotic giant branch. This is done with Gaia Sky, and Gaia Sky also allows to move around the galaxies and look at for example, the bridge and all this. Okay, so one of the things that, well, since this was a demonstration paper with this new data set from DR3, but we already had the previous release with DR2 that a lot of publications were made using this data, including targeting the LMC and the SMC. We wanted to see how much the astrometry improves between one release with the other, because we had 1 more year of observations. This implies reduction of the uncertainties in the proper motions by a half and reduction of the uncertainties in the parallax by 20%. So, and we have more observations. We have gone through each source more than once, so we can, let's see how much the systematics are reduced. So this is exemplified in this plot here. On the top panels, we have data from DR2, and the bottom panel data from EDR3. First column is the colors are the parallaxes, and then it is on the middle and right columns proper motions in each of the directions. So, and then you can see here that we plot in orthographic coordinates. So this is the plane perpendicular to the sky in this direction. So this is X, Y kind of Cartesian coordinates, but it is just in the direction of the LMC, just the plane perpendicular. So these are orthographic, and here we project the proper motions in these coordinates. So this is why you can see here mu X and mu Y instead of mu alpha or mu delta. Okay. But this is just a matter of a rotational projection. But the thing that you have to take from this plot is that in the plot panel you can see a kind of grid, more visible in the parallaxes. You can see that here you can have a blue and red in the middle. You have kind of a grid-like shape that when we go to the EDR3 data, this is more or less disappeared. You have to take into account that the LMC, this is for the LMC, the LMC is about 50 kiloparsecs, so parallaxes are very small at that distance, so we expect them to be around 0. Okay, but you can see that at DR2 we had a large amount of red pixels, which meant negative parallaxes. This meant that the uncertainties in parallaxes were very large, and this has slightly very reduced in EDR3, and now the colors look like more about white, which where we expect to be due to the distance to the LMC. And for the proper motions, even clearer, because here we in the top panel you also see this kind of a grid due to the systematics, and that is basically washed out in the bottom panels with EDR3 data. So you can see how this 50% reduction in the uncertainties and the 1 year of more year of observations have practically removed the systematics in the proper motions. Okay, so the other thing that we wanted to show in this paper, apart from the other plots that are included in them, is the plot as a function of the excess factor. Okay, so this is again a projection in the sky, and the color is this photometric excess factor. We expect this value to be small because it is just the flux of the blue and the red photometer divided by the flux in the G, which is at the broadband. And we expect this to be around 1. And we can see that in very crowded areas, this excess factor in DR2 was large. Basically, you can see here the outline of the bar and the center of the SMC and some globular clusters. But in EDR3 on the right, these values, with the same scale, you can see that these values have reduced now around less than 1.5 or 1.4, something like this. Okay, so again, the photometry in these regions have improved a lot, and this is why we can do this selection of samples, selection of evolutionary tracers. Okay, so one of the things we wanted to do, or we tried to do with the LMC, is try to obtain its 3D structure. But as I said, this was like of challenging Gaia, because to obtain the 3D structure, we need the distance. So the distance, we do not have the distance, we have the parallaxes. And as I said, the parallaxes at these distances are the uncertainties are very large and they are very small. And they are small at the level of the systematics, and they are small at the level of the 0 point we have from the paper of Lindegren. So in the paper, we outline the problems we faced in trying to obtain the 3D structures, basically dominated by this 0 point offset in the parallaxes. And what I wanted to say here at this is that we have not given up. So we're still trying to obtain this 3D structure of the LMC with different techniques, a different fitting method. We're starting from scratch without rush, with a simplified model, and see how we have two different methods that we are trying to see how complementary are one with the other. And we're still pursuing this idea and see how we can save this 0 point offset on the parallaxes and try to obtain the 3D structure of the LMC. So stay tuned, because we are dealing with this. On the kinematics, this is kind of easier. We are only just showing proper motions, and we have seen that the quality of the proper motions are very good. And here I want to show you some a kind of animation. This is the velocity map with a special technique to show the vectors. And this is only velocity map. There is not underlying density at the bottom, but you can see that the velocity hints the presence of the bar here at the center and the presence of the spiral arm in here. If I now overplot, now this is density, so you can see that we could get this piece of arm here, this arm here, and this is the bar. So again, I'm overplotting the density, and again overplotting the velocity field. So this we did for the DR3 paper, and we have not exploited this superposition of plots. And I think we can clearly see the rotation of the LMC disk in here, the kinematics of the bar. So we are there is also work ongoing in this sense. We can try to do the same for the SMC. This is the kinematic field for the SMC. You can see that this is more chaotic. We do not see any hint of rotation in the SMC, but you can see, for example, that this flow of motion towards this wing of the SMC, which is exactly this wing now on the density where the bridge between the SMC and the LMC starts. So again, overplotting the kinematics, maybe they can provide some information on the structure of the SMC. Okay, one of the interesting results of this paper also is trying to determine the kinematic center, the rotational center of the LMC. We can have the photometric center and also the kinematic center. And in this plot, we plot with different crosses the results from different works in the literature with different tracers. These two are from this two, and this one here are from Sky Mapper using carbon stars, RGBs, or young stars. Other works with HST, with the gas. And the ones from this work are the ones in color, and you can see that they fall well within this kind of circle that outline the other works. So I think this is very interesting because it's choosing the center of the LMC or the SMC is one of the key free parameters that then, if we want to undergo with the kinematics of the whole cloud, of the whole galaxy, we need to take into account. So large uncertainties here will provide us large uncertainties in the kinematics of the galaxy. So having a good determination of the center is a key point to study the kinematics and model the kinematics. So I think that we have a well-constrained now kinematic center for the rotational center for the LMC. So once we have this kinematic center, we can try to plot the velocity maps. So in the paper, there are a lot of velocity maps like this. Here, let me show you some of them. On the left here, on the left is this young two population, so upper mean sequence stars, young stars. On the right is for the red clamp in this XY orthographic projection. And on the top panel, we have the tangential velocity, and on the bottom panel, the radial velocity. So our experience in external galaxies and our galaxies, we would expect that the radial velocity has mean around 0. So we do not expect radial excursions around the galactic center if the disk is completely axisymmetric, okay? If we see excursions like these ones of the order of 20 kilometers per second, it is a hint to the researchers that there is something that breaks this axisymmetry. And for example, we can see by eye that we have the bar in the center of the LMC. For the tangential velocity, we would expect to see the rotation. So the rotation is almost 0 in the galactic center. It decreases kind of linearly, and then you can see it becomes more or less flat. This is what we expect for this external galaxy that with this galaxy that rotates with a classical rotation curve. So I'll show you in the next slide the rotation curve. So the 1D rotation curve. Here we have the 2D map. You can see that the differences between the young and the red clamp populations here in these 2D plots are not significantly different, at least for the tangential velocities. The radial velocities, you can see that maybe the pattern is the opposite at the center of the galaxy where we have the bar. So this also can provide us information on the bar of the LMC. And I think from our knowledge, this is the first time that we can do this kind of plots with two different populations with these 2D plots. So the quality of the proper motions have allowed to do this. What we had before is this kind of the typical 1D curve. So this is again on the left tangential velocity, on the right radial velocity as a function of the galactocentric radius of the LMC. And we have different curves here. The colors are for the different tracers, the different populations, the different samples that we have showed you at the beginning. And the data with the error bars and these blue curves are from other works in the literature, which is, I think, if I don't remember wrongly, is the work from Wang. Okay, so you can see that they agree very well at the inner radii, and in the outer radii, in his work has a lot of noise and it has a lot of wiggles. But in our data with the red giant branch, we can get to further distances with showing kind of a flat or slowly decreasing rotation curve. You can also see differences between the populations. So the older population rotates slower than the younger population, which is also expected from the models. If we have a look now to the radial component, so again, this migration or this excursion from the galactic center, we can see that it's not centered around 0, that at the inner radii we have this negative tendency towards to this negative, so going towards the galactic center. We can see also the differences between the populations, and in the outer radial this becomes flat around the 0 value. Okay, so we can have an extension of the influence of the bar also by this kind of maps, of this kind of curves. And you can see that in this case, the plot do not agree very well with the work of Wang. I think that our uncertainties with the proper motions here can do a better work here. In the paper, you have these curves separated by population instead of one, not only one in all of them in one plot. We can separate the populations. We can separate the components. We can also plot the dispersions on these velocities with their errors. Okay, so let me go on. And now we decided to study the region between the two clouds, what were supposed to be the Magellanic bridge. The bridge is the physical connection between two interacting galaxies that are tidally linked. And here we show this connection choosing this young sample, so this young one and young two upper mean sequence stars, young stars. We have concentrated, we have centered the plot on the bridge region, and you can see here on the left with only densities and with this with the help of density contours, we can outline very well the bridge, this connection with young stars between the young and the SMC and the LMC, and how it connects with this arm of the LMC. On the right, it is the same data, but now we also overplot the vector flow. So we overplot the proper motion vectors in this plane. That they indeed contribute. So the bridge is not only physical in positions, in densities, but it also shows that the stars in the SMC are trapped by the gravity of the LMC, and they just follow this arm around the LMC. We are currently also working in this and trying to characterize a little bit more these stars in the young bridge, and I'll show you later with a more evolved population. In here we do the same vector flow plot between here it is the wing of the SMC on the top, and the wing the LMC is here on the bottom, and we can see these arrows show the median proper motion in different cells in this grid. But if we select the stars in each of these cells, and we do some normalized and smooth histograms and smooth distributions, we can see if there is only one population that dominates this vector, or there are different populations. So in the top panel, we show on the right these distributions in chi dot and eta. Chi is this x component and the eta and the y component. For the stars selected in this bin, where you can see the red arrow here, so you can see that this is mainly dominated by the rotation of the halo or the outer parts of the disk of the LMC. So we have a clear kind of Gaussian motion. But if on the other hand we choose one of the bins that is on top of the bridge for the young sample, we can see that now the velocity components are dominated by this flow from the SMC towards the LMC, but we can also have some other contamination by other stars in the outskirts of the SMC. So this is part of the thesis of Oscar Jimenez in Barcelona. We can do the same, or we try to do the same for the red clam. The red clam in density is very difficult to see a bridge or a very clear narrow bridge as we see with the young population, but if you overlap the proper motions, we also see this flow from stars from the SMC towards the LMC. And one of the things that we can see here is that if we were able to, or if we overlap one plot and the other, this the bridge of the young population and the bridge of the red clam is different. It has a different location. It seems to be shifted towards this southern part and broader. Okay, So this is also that's something that we are trying to characterize. Here, the same kind of plot that I showed before from the work of Oscar. Here we select one of the stars that is there in the outskirts of the LMC with a clear rotation, and if we select stars now in between, in the bridge region between the SMC and the LMC with a clear direction towards the LMC, we can see that in this vertical component, we seem to have a bimodality. We expect that this negative component is the one that is dominated by stars in the bridge with this pointing towards the LMC, which is what we would expect. But we also have another set of stars that have a clear positive behavior, which would contribute to this rotation of the LMC. So it is a way to characterize and try to constrain the sources that belong to each of the components. So SMC, LMC, or bridge. So this is work in progress. The other, so if instead of targeting the region between the clouds, we now mask the clouds, we mask the galaxies, and try to show the substructure in the halos, substructures in the outskirts of each of the galaxies. We can see that there are very clear, some of them well-known substructures, like these arms here, the strings here in the SMC, in the LMC. So they are very well seen in density, but also now we have the proper motion, so we can try to characterize them using the proper motion. We have seen that the LMC has a very nice spiral, so this is clear here. Since it's only one armed barred spiral, we do not have the counterpart of this grand design at the southern side. So, and here we have a broken spiral arm with these two sub-arms in here. This is very clearly seen with the young population and the blue loop stars, so very young stars. Now we can select this population and undertake the study, for example, of trying to derive the rotation speed or the angular frequency of this spiral arm. If it is co-rotating, if it has a fixed pattern speed, what theory matches, if it is a density wave or it is a rotating spirals. The same for the bar. Can we constrain the pattern speed of the bar? So these are some topics that we are working currently. So this is mainly for this DR3 paper. I didn't want to spend so much time, but I wanted also to show you some other works. But of course, it is not a very complete and exhaustive work on the LMC and the SMC. There are hundreds of papers in the literature targeting our neighbors, but I wanted to highlight some of them and relating them with the work that we have done with the Gaia data. So I think we can agree that one of the classic works or papers studying the structure of the clouds is this work by Vanderbilt and Chion in 2001 and Vanderbilt in 2001, 2002. So he's got several papers. He's using TUMAS and Denise surveys in the infrared, and in his work is trying to obtain these inclination and position angles of the LMC. We know that the galaxies in the sky do not have to be face on to our line of sight, so they have two free angles, which are this inclination and this position angle. If we want to study the 3D structure of these galaxies, of these external galaxies, these two angles are key ingredients to project them, to put them face on, and then we can start disentangling what is the semi-major axis of the bar or semi-minor axis of the bar or the ellipticity of the disk. So this was one, I think, from my point of view, one of these first works, and this data is still widely used so far. Also, there is I think, a very wealthy survey. This is the VMC using Vista Survey of the Magellanic clouds. This is a survey that started observing in 2009 with the Vista and stopped in 2018. They have more than 40 publications targeting different parts of the LMC, SMC, bridge, outskirts, stream, Magellanic stream, and this. And in the first works, they also tried to constrain this inclination and position angle of the galaxy. You can see the tiles here of the they have covered in the different epochs, and they also have proper motions with Gaia. So let me show you one of the recent works using this VMC survey. So this is targeting the bridge region with the proper motions in the bridge region. So here it is the SMC, the LMC, and the tiles that cover the bridge. And in the background we have the density from the gas, from the neutral hydrogen gas. So they covered the position of this is the wing of the SMC from the bridge, and they obtained using a young sample set of sources from stars the proper motion field. So something similar as we did with Gaia EDR3, but using the proper motions from BMC. So we can also outline this flow of stars and sources from the SMC towards the LMC, and they also do some comparisons with embodied simulations. This is not the only work trying to constrain this bridge with proper motions. There is also the work by Ziv Can collaborators using Gaia DR2 proper motions. So this is from DR2 proper motions. And they also have three fields, these three brown stars that you can see in this plot on the top, which are HST fields. So they also have the proper motions from HST that they overlap here in the bottom panel with the data from the young population, so the blue stars, and the red clump population, so the red stars. So they agree very well with one with the other. Another topic that is also very in nowadays is about the rotation of the SMC. If SMC is an irregular galaxy, this does not show a bar as we can see in the LMC, and it does not have a typical disk rotation component, as also happens with the LMC. And this is corroborated with also these two recent independent works. The one with Ziv Can collaborators. Here you see this velocity vectors for I think it is red giant branch stars in the SMC. They also have a plot zooming in the inner region, and the conclusion is that the rotation signature is not detectable. The same using the proper motions with this VMC survey. Here you can see also the plot, and there is no signal of rotation around the center of the SMC. So this has implications if we want to model these two interacting galaxies with simulations. We can model the LMC as a disk-bath galaxy, but the SMC we cannot use a disk galaxy because it does not show a clear disk rotation. We have also seen that the outskirts of both the LMC and the SMC are very rich. So we have substructure in the stellar halo. So some of which we highlighted in Gaia EDR3, but these are recent works also by Maki using the dark energy survey camera, the CAM, and they also highlight different substructures both in the LMC and the SMC, and also the work by David Martinez Delgado and using Canon data, so photographic data, and the SMASH survey. This is also from 2 years ago, and you can see they highlight this shell, so they concentrate mostly in the SMC, And here you can see this is 47 tuck. This is a well-known globular cluster, but you can see here a kind of shell that then with this with this mesh data, they see not only the shell, they see a kind of spiral arm in here and a kind of also stream in here, possibly linked to a globular cluster. So there is a wealth of information in the LMC and the SMC that now with the quality of the DR3 proper motions, we can try to characterize not only using positions, but also using velocities with the proper motions. And all this data, I think it is important to be able to compare with simulations to understand the behavior we observe in the data. So there are also a wealth of papers modeling and trying to model the LMC and the SMC. Here I'm going to highlight just a very few of them, trying to understand and or simulate the formation of the Magellanic stream. It is a very well extended stream in the sky. So here you can see this is the work by Gurtina Vesla in collaborators in 2012. Here this is the LMC, the SMC. You can see the bridge very nicely reproduced, and this is one of the spiral arms. But you can see this is the Magellanic stream, and trying to fit with the data. Same with the work with Wang and collaborators. So this is data, and this is the models. This is very well nicely constrained. This is also a recent work by Williamson and Martel. Here they have more difficulties to fit the Magellanic stream, but I think it's also very nice work. And also the work by Tepper Garcia and collaborators, where they have different aerodynamic models with taking into account ramp pressure, the magnetic fields, and all this, trying again to constrain the Magellanic stream. Okay, so just to finish, this is if I had to write down a summary or something that I would like to highlight from the LMC and the SMC, is I think that from my point of view, the LMC and the SMC are very well studied and very well characterized photometrically. But now with Gaia, I think Gaia DR2 opened the window to have a large sense of sources with kinematics, so we can undertake dynamical studies in the SMC and LMC, and being able to compare with models. The LMC is a bar galaxy with one spiral arm with a clear rotation, but why does it have a one spiral arm? When we go into the external galaxies, these kind of bar galaxies show very nice grand design two spiral arms. So this is not very well understood yet. What is the rotation speed of the bar? Can we constrain it? The SMC, on the other hand, is an irregular galaxy, which is not detectable. It has no detectable rotation. So is it because it has undergone several passages, or it has a high gravitational attraction by the LMC? So, we can now use different tracers to highlight different characteristics. We can select young, red clams, safe age, or early. I have not shown the works with the safe age and using ogle in the LMC because I cannot show everything, but these are also very nice works. The bridge region it was very well established using gas, but now we can start constraining it with the young stars and start hinting with a more evolved population like the red clams. It is a more kinematically hot population. So it is easy that we cannot see it in density, but we can see it in the proper motions, in the velocity flow. So I think it requires a detailed modeling in this sense. It has a rich, they both have rich substructure in the outskirts. We have shell streams, the Magellanic stream, so the spiral arm. And so Magellanic stream in particular has a large extent, and some recent efforts have been put into modeling and trying to reproduce the stream, but I think we will see more still in the near future. And that's it. Maybe I'll stop sharing.
Okay, perfect, Mercè. Thank you a lot with all the travel, and you gave us a very, very nice talk about the Magellanic clouds. And now we can take questions. Please, if anybody has a question, you can raise your hand, and I can then tell you to start talking. And please, if you can make very short introduction about who you are, just for the other people in the audience, it will be much appreciated. So, if anybody has a question. Nobody? Yep. David Montes, you can start. Yep. David.
No.
Okay. Yep.
I don't.
I think it was me who raised the hand.
No, pero David también. Ah, okay. Nos lo pone a la derecha, vale.
Oh, yes. So Armando.
That's okay. No problem. Well, this is Armando Gil de Paz from the Complutense University. Just a quick question. I mean, I was wondering, when you were talking about the gas in general, mainly from the perspective of the H1, but do you know of any effort to try to use ALMA, for example, for trying to measure in any kind of proper motion also? Because there are around 20 milliseconds, which is for some of the gas components in the bridge, especially could be doable. Especially.
It is a very good idea. So I am not aware of any work using ALMA, but I think it could be a very nice idea for the bridge with this resolution. Yes.
I mean they have something like 20 milliseconds, which is, I think can be in the limit, but especially if you compare with, I don't know, some other observations, or you just give some time between now and when ALMA, yes. 20 years or so, I think might be, I don't know, doable. And the other thing is, do you expect then to have some, because for what I got from your talk, it's very clear all this fall of material to the LMC from the SMC, especially in the young population, but it's not so obvious or not in the case of the old stellar population. So in principle, if you go now to the gas, it should be even more obvious, right? So in the
gas it is obvious. In the gas it is, at least with its 21 centimeter line, it is clear, and it was first discovered in the bridge in the gas, and then it came with these very young OB stars. And then when we go to more evolved populations, then it is more difficult to see. There is a controversy with the error. There are some works using error from Gaia Year 1 that they seek to trace this old what they call the old bridge, but then it was shown that it was an artifact, and then the error work using Ogle did not confirm the presence of the error bridge. But in our case, okay, we agreed that the error bridge is not there, but with the red clown, which is an evolved population but not as old as the error, it's the flow. It seems to be clear. So, but it is difficult to select the stars in the red clown stars in the bridge and put like let's say a line. Because it is since it is kinematically hotter, the dispersions are larger, so it may seem that they are shifted bridges, but maybe it's because of the natural dispersion of the star.
And for example, from the analysis of the position in the HRR diagram, can you constrain whether, for example, this young population is falling to the LMC was formed in situ or was formed first in the SMC and then felt?
No idea here.
I think I was thinking the same, sorry to interrupt, but the ROV stars, they must have formed in the bridge, no? Because what is the time scale for...
Yes.
For the... I don't know the dynamic, how long it will take dynamically.
No, I don't know. But I also agree that they might the they might have formed in the bridge. Or I know there are, but I don't remember who's the author, there are some works that they kind of do a metallistic gradient of the stars in this bridge region. And then they seem to match the metallicity of the SMC. So it may be this kind of wing that maybe they were already born in the wing and they start moving towards the LMC following the bridge because they match the SMC metallicity, but I don't know the timescales that they need.
Thank you.
Okay, some more questions from the audience? I have one related with the kinematic map you showed at the very beginning. That was, you were showing the flows, the flow of the stars, but not the density. This first map that you have shown. For the LMC, it looks like well, first of all, the question: have you subtracted any velocity from this map, or is directly the map of proper motions you observe in the sky? This is the first question. And if not, this means that the Large Magellanic Cloud has a very small velocity with respect to the Milky Way, because you mainly see the rotation. You see no systematic flow.
No, we removed the. We do remove the let's say the bulk motion of the LMC with respect to the Milky Way.
Okay.
This is removed. So what we show here is the motion of the sources in the LMC. So from the LMC point of view, let's say.
Okay, and you did the same for the SMC, because if you go to the SMC,
but the SMC we cannot do the same because the SMC is not a disk, so it does not have a rotation. So for the SMC, you can see that for example, in the paper we do not include it in the kinematic section. Okay. Because this is more tricky. It's not. I think the approximation is not so. It's not appropriate.
Because in the picture you have shown, it looks like clear that there is a systematic motion towards the Large Magellanic Cloud. It looks like. So probably you subtracted the same value for the small and for the big, and in the small this doesn't.
Yes.
This is not the best approach.
Exactly.
Okay. Thanks.
But I didn't do it. It was the team.
Good. Okay. So, any other question in the?
I have a question, but this is just I'm curious about it. I mean, I'm basically observational, so everything related with models always intrigues me. So one of the things is that, I mean, it seems here that in order to reproduce the whole complexity of the system, you are having now a non-asymmetric component, which is due to the interaction with the Milky Way. You have a non-asymmetric component with interaction between them, and then you have the non-asymmetric component, which is the bar itself. So can you put all together in a simulation at the resolution that you need to infer what is actually driving what? So
yes, I'm also getting into this world of simulating interacting galaxies, so I'm reading some papers currently, and what people is doing is when they do some N-body or hydrodynamical simulations is they do take into account the presence of the Milky Way. So either with a static potential or with a dark matter halo, just have it there because they have influence on the Milky Way has its influence on the kinematics of the clouds, and then they generate like kind of two disk galaxies with the masses of the LMC and the SMC, and then they allow the interaction. But most of the people do hydrodynamics, so they take into account also the gas motion and all this. So I think they are rather complicated simulations with these three bodies. But I think because I'm also trying to model this, I think I would prefer to go step by step. So if you want to analyze, for example, the kinematics of the sources in the bridge, so I think the first order of effect on these sources is the fact that they are in the middle of two interacting simulations. So first I would simulate these two interacting simulations, and with a very cold, so kind of young sample. And then as a second order effect, I would or a second step, I would include the effect of the of the Milky Way, which I expect to have an effect. But I think that if you are focusing in a very detailed or very constrained problem or sources that are on the LMC or the SMC, I think the first order effect is the fact that they are in two interacting galaxies.
Okay, so for example, you could pull the Milky Way potential analytically and then numerically put on top the...
For example, or first just simulate two interacting galaxies with these two n-body simulations, and then add either an analytical potential or a dark matter halo of the mass of the Milky Way at a 50 kiloparsecs distance and check its effect.
Okay.
But like going effect by effect, so to understand what is if you put everything together, you will not be able to disentangle if the motion is due to because you have the SMC right here or because of the dark matter halo of the Milky Way. So if you go step by step is when you will be able to understand the observations.
Thank you, Mercè.
Okay, perfect. Thank you, Mercè. And if there is no more questions there are no more questions in the audience, we will leave it here. Thank you a lot for the talk. Thank you a lot for your answers. And also, again, sorry for the problems we had.
No worries.
And hope to see more about your work in the close future.
Stay tuned.
Okay, thank you, Mercè. And for everybody else, we will meet again next week. Next week, we will have Maria Rosa Zapaterio Osorio from the Centro de Astrobiología on Friday at 10 in the morning. Okay, so that's all. Thank you, everybody. Thank you also, Armando. Thank you, Patricia, also for the organization. And we will meet again next week. Have a nice weekend.
Bye-bye.
Bye.
Adeu.
Bye.
Adeu.